I'm Norman Wildberger. Today we're going to have a look at the third problem in our quiz, which was sent to me by a reader. So the problem is, we have a right triangle like this, and we are told that up here, this vertex has been trisected. So these two lines coming down here split this vertex up into 3 equal spreads, or 3 equal angles. And furthermore, we're told that this distance right here is 11, and this one is 5. And we're trying to find out this third distance right here. So naturally, we rephrase everything in terms of rational trigonometry. Let this spread common here be S. Let's let this quadrant be R1, so that's just 11 squared. This quadrant be R2, which is 5 squared. And this quadrant R3 is the one that we're interested in. And what will be useful for us are these 3 spreads which are right here. That one we'll call R1, this spread we'll call R2, and this spread we'll call R3. Now, to start off this problem, there's just a few things I have to remind you of. One is a very fundamental fact just concerning a right triangle. If you have a right triangle, it makes 2 spreads, S and R, and a fundamental fact, which is really Pythagoras' theorem, is that R equals 1 minus S. Or to put it another way, these 2 spreads always add up to 1. Okay, another important fact that we've already talked about in the last few videos is what happens when you bisect a vertex. So here we have 2 lines making a spread of R, and a third line which bisects them, creating equal spreads S and S. And I hope you all remember that the spread R is related to the spreads S in the following way. R is equal to 4 times S times 1 minus S. And this polynomial is called the second spread polynomial. And it plays a very important role in the subject. And there's also a version of that for 3 equal spreads. So if these 2 lines here are trisected, so we have 3 equal spreads S, then the cumulative spread R is this particular function of S. It's S times 3 minus 4S all squared. That's the third spread polynomial. And I remind you that the spread polynomials are a very important and interesting family of polynomials that generalize this sequence. And for those of you who know a little bit about special functions or orthogonal polynomials, they are very closely related to the Chebyshev polynomials. We've talked about them in a previous video, and sometime we're going to go and have a look at some more properties of these interesting polynomials. But for today's problem, we only need to know the second spread polynomial and the third spread polynomial. So we're going to apply that to this picture now. So here's our picture again, and let me remind you what it is that we know. We know this quadrant's R1, we know this quadrant's R2. And we know that these 3 spreads are equal. We call them S, but we don't know what those spreads are. And we're trying to find this quadrant's R3. Okay, so we're going to have a look at these 3 spreads R1, R2, and R3 here and relate them to S. And we do that by using the fact that in a right triangle, the 2 spreads here add up to 1. So this S plus this R3 add up to 1, so R3 is 1 minus S. Now the same logic applied to this slightly bigger triangle, ADC, means that this spread R2 is going to be 1 minus this spread, the spread formed by 2 of these spreads S. Well, that spread is the second spread polynomial, 4S times 1 minus S. So there's what R2 is. And if you expand this out, you'll see that's actually a square. It's a square of 1 minus 2S. So that's what R2 is in terms of S. R1 will be 1 minus the big spread here, the spread formed by 3 S's, which is S times 3 minus 4S all squared. That's our third spread polynomial. And when you expand that out, then pleasantly the result factors like this. Now in these various triangles that we have here, we can use the spread law. So in this triangle here, ADB, the spread law tells us that this spread S divided by the opposite quadrants R1 is equal to this spread R1 divided by the opposite quadrants, which we'll call P2, which is also equal to this spread here, which is the same as R2, divided by P1. There's the spread law in that triangle. And in this triangle AED, also the spread law tells us that S over R2 is R2 over P3, and it's the same as R3 over P2. So we have these two spread laws, and now we're going to combine them, and we're going to express P2 in two different ways. One from this equation and one from this equation. So from right over here, if we solve for P2 and put P2 up there, and bring the R1 over there and the S down here, we get P2 equals R1, which is this expression right here. There's R1, little r1, divided by S times capital R1. That's obtained by solving this for P2. And if we solve P2 from this equation, then it's going to be R3 over S times capital R2. Well, there's little r3 divided by S times capital R2. So having solved for P2 in two different ways, we now get a relation between S and the two quadrants that we know, R1 and R2. Because conveniently the 1 minus S and the S cancel from both sides. And we're only left with 1 minus 4S squared on this side equals R2 over R1. Those are the ones that we do know. We know that R2 is 5 squared. We know that R1 is 11 squared. So we can solve for S. It's a quadratic equation, but we know, because of the problem, that this spread S had better be less than 1/4. 1/4 is like 30 degrees. And if that's more than 1/4, then this cumulative spread with the three vertices like this is going to be more than perpendicular. It's going to be up above there. So we have to choose the value of S which is less than 1/4. And that, once you solve this quadratic equation, is 3 over 22. Okay, once we know what S is, then we're in a happy situation because we can solve for P3. How do we do that? Well, from this equation here, there's P3. If we know now what S is, we know what R2 is because it's given by this expression in terms of S. We know what R2 is, that's just 5 squared. So we can solve this for P3, and that's what we get, 3200 over 33. And now in this triangle ACE, the skinny one, we have the quadrants P3 now. And so our quadrants R3, which is what we're interested in, is going to be S times P3, since that spread is opposite over hypotenuse quadrants. So R3 is going to be S times P3. We have P3, we've got S, we multiply them together, and we find that R3 is 40 over 11 squared. That's our answer in rational trigonometry. To find the length, we just take the square root, 40 over 11, which is approximately 3.6363, and it repeats. So we've solved our third problem. The fourth problem on the quiz, involving the flexible quadrilateral, is quite a lot more challenging. And to solve that, we're going to have to develop some new material on quadrilaterals. Next time we're going to start by going back to Euler, the greatest mathematician of the modern age, and discussing an important formula that he discovered that tells us something about 4 points in the plane. I hope you'll join me for that. I'm J Wildberger. Thanks for listening.